Alright, welcome to CS 4510. This is L11B, and the topic is Russell's paradox. We're continuing where we left off on our discussion of logic, but now let's get a little more formal. So what really is logic, and what is the foundation of logic? The way thought is done in a combinatory sense was really understood first by Aristotle. Again, maybe he was just the first to write these things down. He wrote metaphysics, and also part of this he wrote the Organon. And wrote, among other things, we grant him, influence on, for example, excluded middle and so on. There was also a few millennia pass, and the next person to notice something along these lines is Leibniz. Leibniz is the better inventor of calculus. He worked extensively later in his life on some kind of mechanical calculator, and he noticed that the act of thought and the way that thoughts in the brain may combine themselves into larger and larger thoughts, the way truth is done in an intuitive sense as a deductive process, is exactly like that of mathematics. So I have a quote from him here. It is obvious that if we could find characters or signs suited for expressing all of our thoughts as clearly and exactly as arithmetic expresses numbers or geometry expresses lines, we could do in all matters insofar as they are the subjects to reasoning, all that we can do in arithmetic or geometry. For all investigations which depend upon reasoning would be carried out by transposing these characters by a species of calculus. So he understands thought is actually quite mechanical. For example, when we have, does anyone know the name of this rule? What does this imply? Yeah, why? You did a deduction there, and given two truths, you would derive a new one. But the process in which your brain does that is kind of mechanical, and perhaps could be abstracted away to pure symbolic manipulation. So he notices, okay, numbers are done, arithmetic is done as the manipulation of numbers, and geometry is done as the manipulation of symbols representing lines and angles and so on. So why not all thought can be represented as symbols? These are very modern symbols, but he thought, obviously we can externalize thought in such a way such that the manipulation of symbols by a few rules could be perhaps enough for us to calculate do all reasoning by a transposition, a movement of such symbols. So he was one of the first people to notice this. And important here is this notion of that thought is performed not perhaps as an act of creativity, but as an act of mechanical, some procedure in a very mechanical way. Next came a few other characters. One of them is Piano. Piano wrote this thing called Formulario Mathematico, in which he tried to create relatively close to a modern system of logic in which mathematics could be done by a manipulation of symbols. And this is prior to anything else that had been done at the time. And he also worked as a calculus teacher, and he had some idea in which all mathematics, a teacher could be perhaps replaced by someone who simply manipulated the axioms in such a way to derive truth. And he tried to teach a calculus course this way in a pure logical sense by doing propositional logic for everything. Today we would call this propositional logic, but he tried to do such a thing to teach a calculus course, and he was fired almost for attempting such a thing. It's too mechanical, it's too not good, but it notes a first attempt at something like this. And Piano was also we'll talk about Piano later today as well, but he was also one of the first people to notice a very important distinction in concepts. So consider we're dealing with sheep, right? Suppose there are really two notions of sheep. First off, there is an object that is a sheep. So we may say something like X is a sheep. And then there is also the notion of X is sheepness, right? Sheepiness, in the sense that X embodies the property that is sheepness itself. So there's a distinction to be made here between an object having a property and the object being a property. in the sense that sheepiness as a concept is something perhaps prior and greater to that of an object being a sheep. Today we formalize this with set theory, right? So we say, for example, X is a sheep to mean something like this, where S is the set of all sheep. When we say this, we mean X is an element of S. You know how to read sets. So we say that if S is the set of all sheep, then we know that X is a sheep, right? But this is distinct, this notion is distinct from that. And that's today how we conflate these two. We also understand set theory in a very modern way, but these guys did not have this. They had a very primitive, naive set theory, in the sense that we understand this to mean in, right? And that we have, for example, sets act upon each other the way Tupperware may have containment. And that this is S, and then we put X there, right? X is in S, as in a containment relationship. But this is not the original notion of set theory, and this is in fact a modern one. The original, this symbol E actually stands for the Greek word, I'm going to butcher this, iota, I think, which really means, does not mean in, but it means is. So what this really is not a containment operation, but rather one of type declaration. So this is much closer, when we say X is S, this is much closer to that of a programming language performing a type declaration rather than a containment operation as understood in set theory, modern set theory at least. Because what if S is, for example, S is the set of all sheep, then X is S means X is a sheep. You're saying that X is a sheep. It's the type of sheep, right? It did not mean in, it meant is. Piano was the first to perhaps understand this. Question on that? Okay. Another guy came along and he really carried the mantle and was really the first member of this, what we would call the analytic tradition. Frege was the first to really carry forward Leibniz's program in the sense of creating symbols which, through manipulation of those symbols, model most thought. So he has a book, it's not too long, it's called Begriff, I'm going to butcher this, Begriff Shift. And he creates a modern notion, am I going to spell this right? Begriff Shift. The modern notion of basic propositional logic as we would define it today. So some of the rules that he defines are, let's see, do I have them? Yes. So for example, many of the modern rules of deduction we have come from him. For example, A implies not A. Important to know that it's not given as an if and only if. If A equals B, that implies f of A equals f of B. Again, you can just say that's true and you may not know why. It's because it's an axiom. Another one is like if A implies B is true and A is true, then what must be true?
B is true.
Why?
Because A implies B.
I guess I'm asking, do you know the name of the rule? Fancy Greek words, modus ponens. Modus ponens was and in some sense, all rules of deduction are just transformations of modus ponens. Modus ponens is a very prior and important concept. Importantly, in his set theory, he also defined two axioms, which are taken as part of naive set theory. First, I'll tell you the axiom, and then I want you to tell me what it means. It's called the axiom of existentiality. Existentiality. I hope I spelled that right. Cool part about being a logician and a mathematician in general is that you get to use big made-up words and cast them like spells. So continue part of that tradition. The axiom states, for all x, for all y, for all z, such that z is in x, if and only if z is in y, implies that x equals y. This is the first axiom given by Frege. What does it state?
Two sets of the same elements, then they must be the same.
this is in fact the definition of equality of sets. Two sets are equal if they contain the same elements. So such a containment operation as a relation is defined upon sets which are themselves meaningless. And X is an X, for all Z in X, Z is an X if and only if Z is in Y, means that every element in X must be an element in Y, and vice versa, every element in Y must be an element of X. That's in fact, you can cast the double set containment from this by taking this if and only if and getting P implies Q, right? We know that P if and only if Q is logically equivalent to P implies Q and Q implies P, right? So you could apply such a rule to get the double set containment definition of equality of sets. But this is just the definition of equality of sets. The second rule, I'll tell you, is called unrestricted comprehension. There are other ones, but these are the ones we'll focus on today. And it states, let me make sure I get this precise. There exists a Y for all X such that X is in Y if and only if phi of X. All this is really saying is for any predicate that you can define, any phi, that there must exist a set of elements that satisfy that predicate. That's all it really says. And this is not so different than our modern set builder notation. In fact, this really is our set builder notation. For X is an element of some universe of discourse, for phi of X to be true, that's just the notation we use to construct a set of objects satisfying certain properties. So some set Y exists that X is in Y if and only if X satisfies some criterion. So for example, suppose our phi is defined over natural numbers, and we define this to be, there does not exist a Z such that Z is less than or equal to X, and it is false that Z is 1, and it is false that Z is equal to X, and it is true that Z must divide X, and X must exceed 1. Suppose I have defined such a predicate over the natural numbers. If I were to apply unrestricted comprehension, what set would I get? I guess the more prior question is, what numbers satisfy such a relation, such a predicate? For what numbers, natural numbers, can you plug into phi here to be true?
Z has to divide X.
There does not exist a Z such that those four things are true.
Oh.
Unless I made a typo, I'll just tell you guys this is the definition of a prime number. A number is prime if there does not exist a number that divides it that's not one in itself. So that's just the definition of a prime number. So we may apply unrestricted comprehension with this constructed predicate phi to deduce that there exists a set of all primes. Now note the set of all primes is different than a number being prime. That is an object that we've now constructed which is different than any individual prime number. A set of primes exists. Unrestricted comprehension. Not particularly too controversial, would you agree? It just lets you make sets of things. So this is kind of what Frege system was about, and again, this is modern notation. He was nothing like this. We'll show you some of his notation later today. This all followed part of the formalist dream, which was known as Hilbert's program. Hilbert's program, and Hilbert had his name shows up quite often. He sought to put mathematics on really granite foundations. And so he desired the 4 properties for any mathematical system. First, a formal language. It was understood quite early on that the English or any specific language is ambiguous. There are sentences with meaning that is imprecise, in the sense that a sentence by 2 different speakers could mean two totally different things. So we need to eliminate the use of natural language and construct with our own language. And we do so, today we would say that we construct such predicates according to something like a context-free grammar. But he wanted some language of symbols which was independent of prior meaning. And today we use the symbols that you all know, quantifications, implications. These are all part of that formal language in the sense that such a formula cannot be misunderstood. There is no ambiguity here, there is no, adjectives or whatever. This is like pure. And the construction of what are called well-formed formulas is important in the sense that these are the symbols that are meaningless that are to be manipulated. So first he demanded that mathematics be founded upon a formal language, not a natural language. 2, completeness. Completeness asserts that there is a perfect and beautiful correspondence between the notions of truth and provable. So something is true if and only if it is provably so. So if something is true, it must be able to be demonstrated that it is true, such that the demonstration occurs following the axioms and the laws of thought, and the laws of thought are themselves axioms. Combining these together gives you the deduction of a statement. So if something is true, there must exist a proof of it, and anything that can be proven must be true. If you can prove something, it is true. If something is true, there must exist a proof that it is true. Those 2 notions have to correspond perfectly. That's the notion of completeness. 3, consistency. Not only, a system is said to be inconsistent if it can prove a falsehood. So any axiomatic system, AS, is said to be consistent if it cannot prove 0 equals 1, right? But not only did he demand that the axiomatic system not be able to prove 0 equals 1, but you must be able to prove that it cannot prove 0 equals 1. So in some sense, he was asking for the axiomatic system to prove the consistency of the axiomatic system. Where the consistency of the axiomatic system encodes the fact, this is some logical statement which is expressed in the formal language, which says that there is no proof of 0 equals 1. Which is not too hard to construct, but and maybe we'll do it later. But what he's asserting is he wants a proof of the consistency. Proofs of consistency are not particularly controversial because Euclidean geometry, first 4 postulates can be proven consistent. Postulate with the parallel postulate can be proven consistent, as well as the negations of the parallel postulate can be proven consistent. In the sense you can prove they can't prove 0 equals 1. That can be done. And so he demanded consistency of such a system as well. Now notice consistency is much more important necessarily than completeness. Because if a system is not consistent, then just throw the whole thing away. I mean, everything can be proven and not proven. There's no point, right? It's known as the principle of explosion. If you can prove 0 equals 1, then everything is both true and false simultaneously. Maybe I'll demonstrate it real quick. Suppose there exists a single statement, P, such that it is true that P is true, and it is true that the negation of P is true. Given a single statement that is both true and false simultaneously, we can prove and disprove everything. Let Q be any statement at all, okay? We want to demonstrate Q. So first, if P is true, then we know that, what do we know is true? We know that P or Q must be true. Why? Does anyone know the name of that law from propositional logic? It's got a boring name. It's called addition. If P is true, then P or Q is true. Do we agree? We also know that the negation of P is true, right? If the negation of P is true, and P or Q is true, what do we know is true? There's another law that lets you combine these two. I don't know if we remember this. I actually forgot the name of the law. But if these two things are true, forget this first line. If these two things are true, what must be true? Yeah. Therefore, Q. Now notice we proved Q. We don't know anything about Q. We don't know what it is, just basic applications of the laws of propositional logic. We can demonstrate the truth of anything. And in fact, this would also work by similar argument to demonstrate the negation of Q. So everything can be proven, and everything can also be proven true and false. The black hole consumes everything. There's no notion of truth anymore. So consistency is very important. If you don't have consistency, then you don't have any notion of truth because it's completely, it obliterates everything. Q could be, for example, sky is blue. Q could also be the sky is not blue. So the sky is both blue and blue, you know, blue and not blue at the same time. It's, there's nothing to preserve here. The fourth point, any questions on that? This is called the principle of explosion. There's other ways to demonstrate it. This is just the one I remember. The fourth point is something known as decidability. In that given any theorem T, there exists a procedure to determine, if T is true, there exists a procedure to determine the proof that T is true. And this is a very strong point. He wanted mathematics to be highly mechanized in the sense that a proof could be carried out in a very mechanical way. And a sequence of rules of deductions could always be determined to prove the truth of such a statement, right? Now, the power of this comes from the fact, like, many theorems can be expressed in formal logic, but are difficult to prove in formal logic. So a mechanization of such a way would be of an incredible use to mathematicians because it would take their job. For example, suppose we had a statement of the form, for all n, there does not exist a, b, c, such that n is greater than or equal to 3 implies a to the n plus b to the n is equal to c to the n. I hope I got that right. Right. Does anyone recognize this? Yeah, it takes only a few symbols to express Fermat's last theorem in formal logic. That's all you need to do. And perhaps he was hoping that given he didn't have a notion of algorithm yet, but he was hoping that given a, somehow in the system of logic, we would have a discovery process for what proofs were because we knew how to express the theorems formally, the statements of the theorem. So hopefully we could just express the proofs of the theorems just as simply. Now we know that this proof is very difficult to obtain. It took 400 years for people to figure this out. But statement of the theorem is quite simple. And I hope there's not a typo there. I hope I got that right. Right. What we're really demanding here is, in some sense, an explication, right? So we talked about the Church-Turing thesis in the sense that you have some pre-scientific cognitive notion of, let's say, computation. And following the Church-Turing thesis, you can explicate this to become the Turing machine. We gave such an argument in favor of this, right? That the Turing machine is a formal notion which captures the intuitive notion of computation. Now, that's really all logic is. And logic is that you have some prior pre-scientific notion of what thought is, reasoning, rationality, and we would hope to capture this by logic. So that's really all, it comes before the Church-Turing thesis, it's invented before this, but logic is supposed to be a formalization of the intuitive notion of reasoning and rationality and thought, the same way the Church-Turing thesis is a formal notion of the intuitive idea of computation, right? That's what we're hoping to do with Hilbert's program, right? So these are the goals he set out. Right. Piano, any questions on this? Okay, Piano gave an axiomatization. So again, what is an axiomatization? Is that you take finitely many samples of the human experience, you construct a set of axioms, and then you hope that they correspond. Every theorem provable from such a set of axioms corresponds precisely to the way you understand the intuitive object to work. So Piano gave what he's most known for is an axiomatization of the natural numbers. So this is called Piano's arithmetic. There are 10 axioms. First, there exists 0. Okay, zero exists, it's controversial but true. By the way, in a philosophical context, if you don't have a set of axioms, then you may not derive any truth. Ancient Greek idea is that truth may only be derived from other assumed truths. So you need to start somewhere, so let there exist zero. Next, I'll give you three axioms, I want you to tell me what they say. For all x, it is true that x equals x. For all x, for all y, it is true that x equals y implies y equals x. And for all x, for all y, for all z, it is true that x equals y and y equals z implies that x equals z. What do these three axioms state? Yeah.
That if two or more numbers are equivalent, they're the same number?
Yeah, but I'm looking for, do you know the name of these properties? This is an equivalence relation, right? What he's saying is equality is reflexive, symmetric, and transitive. It is true that x equals x. It is true that the equality is commutative. X equals y implies y equals x. And it is true that equality of naturals is also transitive. So if x is equal to y and y is equal to z, it must be the case that x is equal to z, right? Again, very simple prior notions. Let's see. For all x, for all y, if it is the case that x is a natural and x is equal to y, then it must be that y is a natural. What does this axiom state? First off, is it true? Is this fifth axiom of piano arithmetic true? Why?
It's true, we don't need it as an axiom.
An axiom, I guess there's two questions. First is the axiom is always true. It is assumed to be true, and the proof of the axiom is itself just it's an empty proof, right? Because the proof is, we assume the axiom to be true. So we write down the axiom and then say QED. That would be a valid proof. I'm also asking two questions. One, we assume it to be true because it is an axiom. But two, it's an axiom because it sounds like it works. It looks like it makes sense, right? Is there any kind of objection to that this is intuitively true, in the sense that our understanding of how quantity works, as we formalize the natural numbers, to correspond to the intuitive notion that this captures that?
It looks true.
Yeah, that's good enough. That's all I need. Okay, for all n, if n is a natural, then it must be true that the successor of n is a natural. The successor is some function defined. We usually say the successor of n is equal to n plus 1 in an arithmetic sense. This says that the naturals are closed under succession. The successor of a natural must be a natural. For all m, for all n, if s of m is equal to s of n, what must be true? Extend your intuition. Yeah, why? That sounds right. So we take it as an axiom. There does not exist an n such that the successor of n is equal to 0. No number is the success. There is not a number such that its successor is 0. 0 is the least number in some sense. These are all we really need for the axioms of arithmetic, and it's like that's it. I mean, like that's all you need for natural numbers. It turns out that he gave a very precise axiomatization of the naturals. That's it. Now we want like a model of this. We want somehow to implement the naturals. So back in the day, people were like finding axioms for Euclidean geometry, and that would be a separate thing. And then we were finding axioms for set theory, and that would be a separate thing. And then we had axioms for number theory, and that would be a separate thing. And then all these different, what math you were working under had different axioms, right? But it turns out that set theory is so powerful that you don't need separate axioms for every branch of mathematics you work under, because every set of axioms can be taken as theorems from a set of axioms for set theory. Now you understand this intuitively to be true because everything we've done is sets. Strings are defined as sets, languages are sets of strings, and everything is built upon the language of set theory. But we can prove that, in fact, that if you have number theory, you cannot take set theory as theorems. But if you have set theory, you can take number theory as theorems. So if you had to choose one, you can always choose set theory. I'll demonstrate to you that we can prove Peano's axioms as theorems of a set theory. So what we need to do is construct sets that simulate numbers in some sense. What are the real properties of the naturals that we need? First, we need a zero. Something must exist, controversially so. Zero is a natural, but it is there. And it is defined to be such a natural axiomatically. Then the remaining naturals are defined in a successor, in a pattern of succession, right? Whenever n is a natural, so is the successor of n, and so on. The naturals are produced in such a way, so if we want something that is the naturals, all we need is two things. We first need a zero, and then we need a successor function. Okay. So we proceed now by what's called the von Neumann construction of ordinals. And ordinals are simply sets that pretend to be numbers. So we want to make as few assumptions as possible in order to have a better and more aesthetically pleasing system. So rather than have a jumble of axioms that might argue with each other, we want to create a very simple system. So we first need to define that there is a zero. So we need zero to exist. In the beginning, there was nothing. There is no assumptions. Okay. But we are still able to reference nothing. So although nothing exists, the reference to nothing is itself a kind of something. Therefore, something exists. Suppose nothing exists, we reference nothing, that is something, therefore something exists. Agree? Okay, something exists. Let that something be zero. If you suppose further we have the axiom of unrestricted comprehension, what is the best set you can think of to represent zero? Let zero just be a shorthand for a set. What set ought to represent zero? Yeah. We are not given the empty set as an axiom, but in fact we may construct it as a theorem following unrestricted comprehension. Why does the empty set exist following unrestricted comprehension?
Make their phi 0 or false for all x.
Yes, let this predicate be any predicate which has no elements which satisfy it. Then there exists a set with nothing in it. Therefore, the empty set exists. Done. Okay. We have now constructed a zero. Now we need some set to be 1. Okay. Now we can't have 1 be the empty set because 1 is already not the empty set. Sorry, 0 is already the empty set. So we need a different set to be the set which represents 1. We need some set to be something defined as a set which is not the empty set. Okay? If the empty set corresponds to nothing, we want a set that corresponds to something. So let us construct a set which contains the only something that we know. The set which represents the number 1 is itself a set of something which is the reference to nothing. Because something is not nothing, we have a something which is different than nothing. We have constructed a set which is not nothing. Okay. We need a set which is distinctly different than nothing. It is not nothing, and it is not the reference to nothing. We need something that is not nothing and not the prior something. Yes?
It's a set of nothing and the set of nothing, but that's containing the set.
It is the nothing and the reference to nothing are two distinct objects, which are our set of two, okay? We have our successor function. The successor of any set, let's say W, is going to be, we'll call it W here, is going to be a W union the set which contains W. That'll be our successor function. We'll show that it has the properties that we want. I'll just give you the next few. These are called ordinals. Ordinals are sets that pretend to be numbers, but they're pure sets, okay? What is the set containing 3? It's going to be the nothing. We need 3 objects. It's going to be the something, and then the set which contains the nothing and the something. Is that right? Okay. The set which represents 4 is the nothing, the something, the set of the empty, which contains the empty set and the set containing the empty set, and the set which contains the empty set, the set containing the empty set, and the set which contains the empty set and the set containing the empty set. Okay? Please don't make me write 5, but you can see that we have, in a pure set theory sense, we simply have references to other, we don't have any numbers, okay? We're working in a system that does not have numbers, and we're defining numbers. We can't even assume numbers exist, but yet through just the reference that sets have to each other, we can construct objects that behave like numbers. These are what are called the von Neumann ordinals. And these are sets that simulate numbers. Now, this is not the only construction of the naturals in pure set theory, but it exists. Now, importantly, we get all the axioms that we want, right? Convince yourself that every axiom can be taken as a theorem of, every axiom of piano arithmetic can be taken as a theorem of some axiomatic set theory, such as Fredge's system. The 2 most important relations that need to be defined on naturals are what? The equality relation and the ordering relation. We need to be able to order naturals, and we need to be able to define equality of naturals. So let the numbers I equal to j, we define the equality of naturals to be true if and only if. What should be true about their sets?
What are those about? Every element's equal.
Let OI be the ordinal so we don't get these mixed up. There's a big difference here. That is an equality of sets. That is an equality of numbers. So the equality of numbers is defined to be that which is their ordinals are equal, but the definition of the equality of these sets comes from the axiom of existentiality, where 2 sets are equal if and only if they contain the same elements. For example, we may use this definition to prove 1 equals 1. Let's prove 1 equals 1. Is it true that for all z in the set which contains the empty set, that is z if and only if z is an element of the set which contains the empty set? Right? So let z be an element of the set which contains the empty set. Then we know that z is equal to the empty set. So that implies that z is an element of the set which contains the empty set. Do that both ways, you get that 1 equals 1. Done. Okay? We proved 1 equals 1. What about, when should it be true that the ordering exists? By the way, you get the other axioms about the equivalence relation of the equality of natural numbers from the fact that this, from the axiom of existentiality, is an equivalence relation. You could prove that the sets are equal to themselves, that it's it's symmetric and it's transitive as well. That all follows from the axiom of existentiality. When is it true I is equal to j? What should be true about their sets? Their ordinals? This is a tough question.
Containment.
Yeah. So we have a relation defined on sets, and in fact we define the successor, the next number, to be the set which contains all previous sets. And in fact 1, if you think about it, if the empty set is 0, this is really the set containing 0. This is the set containing 0, 1. This is the set containing 0, 1, 2. This is the set containing 0, 1, 2, and 3, right? If you were to use the shorthand for those. So in fact, the next ordinal, the successor, is defined to be the set which contains all previous ordinals. Conventionally, 3, being an ideal concept, is represented by this set of three objects. It has threeness about it, right? So this ordinal is highly three because it has three things. How convenient for us. We may define the ordering of ordinals if one contains the other, because the set of four is defined to be the set of the previous four numbers. How convenient. So this is the von Neumann construction. You don't need a separate set of axioms for, it may be convenient in like you're doing a proof or something. It's like, but we're not concerned with that question. We're concerned with the foundation for all mathematics. So we have now a foundation from set theory. So we stick with set theory. That's what we're concerned with. Questions on this? So let's do it. Let's do it here. Suppose we are working in a version of naive set theory that is exactly that of Frege's system, right? We have axioms of unrestricted comprehension. We have the axiom, I'll just erase it. It's fine. We have the axiom of existentiality, right? We can deduce anything that is allowed to be a well-formed predicate, right? So suppose we have just these two axioms, and this is existentiality. I guess I spelled that wrong. Whatever. We can apply unrestricted comprehension to anything that we're allowed to make a well-formed predicate of. So consider that we have the set, the predicate which defines sets such that it is false that x is an element of x. There's nothing that, I mean, in modern set theory, that would not be allowed, right? You would argue, no, it is false for all sets that x is an element of x. But we are working in a naive prior set theory where this is not an in relation necessarily as it is a is relation. And many objects are of the property being is and not the property being in. For example, ideas, the set of all ideas is an idea. So is the set of all sets. That's a set. And it may be true for some sets that we wish to define that this be true. Now suppose we apply the unrestricted comprehension to construct a set of all sets that satisfy such a predicate. So what is the set of all sets that do not contain themselves? We may say that there exists a y for all x such that x is an element of y if and only if such a phi of x is true. And we may apply such a predicate to get that it exists a y for all x is an element of y if and only if it is false that x is an element of x. Excuse me. Okay? Now, if it's true for all x, this is true for all x. We've deduced this so far. Now, if it's true for all x, it's also true for some x. We may apply specification. So if it's true for all sets x, it's also true when x is equal to y. So let us perform specification and derive that the special case that x is equal to y. What are we going to get? We will get that we simply symbolically replace every instance with x with that of y. Thank you. We get that y is an element of y if and only if it is false that y is an element of y. Okay? Contradiction is what I would say if we were working in a proof by contradiction. But we're not. I never began this argument with the statement, assume to the contrary anything. Nothing is assumed to the contrary. I've just proven that 0 equals 1. Something true, we don't know which one is true, but something is true if and only if it is false. So, by the principle of explosion, we can prove that any system that has these basic properties is in fact inconsistent. This is known as Russell's paradox. If we were to express such a thing in human language instead of the formal symbols of Frege's system, the question we would ask is, does the set of all sets contain itself? If the set of all sets, sorry, not the set of all sets. Does the set of all sets that do not contain themselves contain itself? If it is an element of the set of all sets that do not contain themselves, then it does not contain itself. Contradiction. But if it does not contain itself, then it must be an element of the set of all sets that do not contain themselves. Again, a contradiction. This is a classic example of self-reference, right? What is the name of this proof technique specifically? Yes, there is in fact, we will use this technique multiple times. This is, oh, hold on, my thing is running out, let me see. This is diagonalization. A cheetah has its spots, and a proof by diagonalization has as many tells. First off, there is some sort of self-reference in a negated way. We ask immediately about sets that it is false for them containing themselves. Negated self-reference, right? Next, we inspect some kind of diagonal. Where is our diagonal going to occur here? It is the case when we consider x to be y, right? If I were to, instead of writing x and y, if I were to write, say, xi and xj, when we consider x equals y, we're really considering when xi equals xj, which is, in some sense, if we were to enumerate them in a row and a column, that would be the diagonal entries, right? So the specification of when x is equal to y is exactly like inspecting the diagonal elements, which is what goes on here. This is a classic example of a negated self-reference. And this is an ancient paradox. So I have a few. If someone says, for example, this sentence is false, this is a canonical example. Basically, all Russell did here is look at examples like this and express them in the formal logic, which, if logic seeks to be a formalization of thought, it should be able to express such statements in the formal symbols. Because this can be expressed in English, why not express it in logic? This sentence is false is declarative, so it is either true or false. And if it is true, then the sentence derived from it is true, which is that the sentence is false, but we assumed it's true, so it can't be false. Yet if the sentence is false, we know its negation must be true. So this sentence is, if the sentence is false, then it is false that the sentence is false, so therefore it must be true. So this sentence is true if and only if it is false. Paradox, right? Most paradoxes upon inspection are not real paradoxes. They're simply notions of impreciseness in expressing them, something like this. Something is hiding in the shadows. Zeno's paradox and so on. But Russell's paradox is a true God-given paradox. And it applies to any system. What's the problem here? The problem is unrestricted comprehension. Any system, any axiomatic system that has a notion of unrestricted comprehension must itself be inconsistent. You can always construct such a statement like this, and bing, bang, boom, you're out of the game. Now, this was devastating to Frege, because Frege, I mean, this is like the worst case thing you could do. He spent several years of his life writing this manuscript, trying to get it published, and only to find that in the last hours before he went to the press, was there such an issue? And by the principle of explosion, this is not something that could be self-contained. The whole thing was wrong because it had such a bug, right? I'll give you another one. A traveler has fallen among cannibals. This is actually from Don Quixote. A traveler has fallen among cannibals. They offer him the opportunity to assert a sentence. If it is true, he is boiled, and if it is false, he is roasted. What should he say? So he can say a sentence. If it's true, he will be boiled, and if it's false, he'll be roasted. What should he say?
It will be boiled and roasted.
It need not be that complicated. He could be both. If the sentence is true, he will be boiled and false roasted. The answer I'm looking for is that he should say, I will be roasted. Because if it is true that he will be roasted if he is saying something that is false. So if he says, I will be roasted, it will be true if he was saying something that is false. And he will be boiled If he is boiled, he is not roasted. So if what he says is true, he will not be roasted. So it is false. And this is how he escapes, the cannibals, something like this. I have one more quick thing to show you. Let's see. Is this thing on? Does this work? Yes. So let's turn this to on. Give me a second. Okay, let's just try both. Eco mode, come on. Let there be light. Okay, let's do this. Infinite loop. But we'll do
We'll cover it.
we'll do that.
Oh,
Did that work?
that works.
Okay, DocCam. Okay, nice. This is a graphic novel by, it's called Logic Comics. It is by several Grecians, including Christos Papadimitriou. We mentioned his name in a previous book. This guy's written so many things. And this is a graphic novel based on the life of Bertrand Russell, which, as you may expect, being part of the intelligentsia, it's actually not that interesting. But also I have this. This is the 50-pound note that they put Alan Turing on. You can see there's some configurations they put on, this is, their fake money. But there's some sequence of configurations that they don't really understand what the graph is, what's going on here, but they put this on the 50-pound note. And then I have a fake version of the fake money, and then you can see it doesn't have the thing in this 50 pounds. But here's the real fake money, and it has the configuration, something like this. So they put him, it doesn't make up for killing him, but they put him on the 50-pound note. Anyway, so part of this goes through the life of, and there's a lot of fourth wall stuff. So Papadimitriou, although being an author, appears to talk to the audience directly. A lot of this is Bertrand Russell giving a speech, and he's talking to himself. So here's him learning Euclidean geometry and deductive proof from his teacher. His parents died, rich boy stuff. Let's see. So here is an example of the notation that Frege used originally. You can see it's kind of tree-like. Today we would do implication. P implies Q implies R and so on. That's all this really is here. But you can see it's kind of a complex set of diagrams. And in fact, I have also some screenshots from his original work just to show you what some of these diagrams used to mean. So here's something, it's kind of, you can see there's the word contradiction kind of going here, and he invented many of the rules that we use in propositional logic today, but his notation was too cumbersome, so we rewrote everything. But he was the one really to invent this stuff. And here is Bertrand Russell meeting Frege, and Frege, I think, is an anti-Semite, and he's very crazy and old at this point, and Russell is trying to do his thing. So what happens is, and I'll read you let's see where it comes in. He meets Cantor. Cantor is also old and crazy at this point, and then he has a nightmare. He wrecked the foundations of mathematics. A lot of cool graphics. Let's see where it can go. So let's begin here. Sets, you say. I thought you were interested in numbers. In my research, I made use of the simple ideal of the priest of Bolzano. I am, but sets are the basis of number. Oh, what is 3 but the set of all sets with 3 elements? Threeness, the common property of 3 umbrellas, 3 horses, 3 hats, 3 cookies. Sets have most interesting properties. Really, and I thought them boring. For example, a set can contain other sets, or even itself. How can it contain itself? The set of all sets The set of all ideas is an idea. Therefore, it contains itself as an element. But not all sets contain themselves. No, the set of all birds is not a bird. I say that's an interesting dichotomy. The sets of sets which contain themselves and the set of sets which don't. About which we can ask, does it contain, and he has his eureka moment. In my life to date, I have written dozens of books, hundreds of articles, I've given thousands of lectures, but I suspect my name will survive, if it does at all, for a confounded paradox that I discovered that year. A paradox that brought logic upside down. I'll give you a taste of it. Imagine a town with a strict law on shaving. By it, every adult male is required to shave daily, but is not obligatory to shave yourself. For those who don't want to, there is a barber. In fact, the law decrees, those who don't shave themselves are shaved by the barber. Those who don't shave themselves are shaved by the barber. Sounds innocuous, however, if taken literally, it leads straight to paradox. For you see, the question arises, who will shave the barber? He obviously cannot choose to shave himself, for being the barber, it would mean that he's shaved by the man who shaves only who. Being the barber, it would mean that he is shaved by the man who shaves only those who don't shave themselves. But he can't go to the barber, for again that will mean he'll shave himself, for which the barber isn't for. Do you see the problem? I'm not sure. It's very much like the paradox of the liar. Which liar? The famous pronouncement of Edubiles, the man who said, "My fellow citizens, I am now lying to you." Think of it. If he is lying, then he is in fact telling the truth. And if he is telling the truth, he is lying. When something refers to itself, paradox is nearby. Take self-referential books, for example. Reference books. No, books that include reference to themselves, like Stirner's Tristram Shandy, Calvino's If on a Winter's Night, and If on a Winter's Night Traveler, or Kurt Vonnegut's Breakfast of Champions. Of course, Logic Comics is also self-referential. Suppose now you make a complete catalog of all books that are not self-referential. It will be a big catalog, sure, but the question is, will it contain itself? And so they're thinking about it for a second, and she's got it. If it doesn't, then it does. If it does, then it does not. And if it does not, it does. The student gets an A+. So what's this got to do with Russell's paradox? Like the examples, it has self-reference at its core. Does the set of all sets contain itself? Does the set of all sets which do not contain themselves contain itself? To which the answer is, if it does not, if it does, then it doesn't, and if it doesn't, then it does. Voila, Russell's paradox. It sounds like parlor witticism, but it subverts the notion of a set as a collection defined by a common property, and with it all logic. So here he's talking about unrestricted comprehension, right? The publication of my paradox made me an overnight celebrity in international mathematical circles. Some greeted it with joy, like Poincaré, who saw in the paradox strong arguments against any attempt to create a purely logical foundation for mathematics. His oft-repeated credo that logic is barren now found a perfect justification. Actually, it's not barren. It breeds contradictions. Haha, this Russell hit two birds with one stone. Logic and set theory are both destroyed. Rather surprisingly, Cantor's reaction was also quite positive. Therefore, if we take the property S belonging to S and consider the negation as defining the set, of which sets do not, glory be to Almighty God, I'm a free man at last. Don't you understand? The Englishman proved the set of all sets is an impossibility. My monster, the usurper of God's absolute greatness, thus no longer exists. Given the right amount of irrationality, one can even read religion even in logic. I'm saved, and so they take him inside. But in the pro-set camp, there was bewilderment and consternation. Logicians were devastated. Giuseppe Piano in Turin, non-impossible, non-impossible, non-impossible. David Hilbert in Göttingen, there must be some way around this, Herr Professor. There must be, damn upstart Brit. And of course, Gottlob Frege in Jena. He read my paradox on the very day he was to give the go-ahead to print volume 2 of his Foundations of Arithmetic. In an instant, he realized the importance of my discovery. Frege, too, had built his edifice on the ground of Bolzano's simple idea of set. And now he had seen that this ground was rotten. It had given way. By implanting sets into logic, he had injected a lethal canker into its body. So the foundations of arithmetic were unfounded. Don't be late for dinner, Gottlob. What? Destroy the printing plates? Immediately. Don't you see it's wrong? It's a disgrace. It's a grotesque sham. Her professor, we slaved on this for years on end. If you don't take pity on your work, at least consider mine. I implore you, don't do it, sir. In the end, he did publish volume 2 of the Foundations of Arithmetic, but with an addendum. Of all the acts of intellectual honesty I have witnessed in my life, none compares with Gottlob Frege's reaction to my paradox. There cannot be greater intellectual courage than this to put the truth above all else. So the addendum says, hardly anything more unfortunate can befall a scientific writer than to have one of the foundations of his edifice shaken after the work is finished. I was placed in this position by a letter of Mr. Bertrand Russell, just when the printing of this volume was nearing its completion. The collapse of one of my laws, to which Mr. Russell's paradox leads, seems to undermine not only the foundations of my arithmetic, but the only possible foundations of arithmetic as such. So, Russell himself is a logician. He still believes in logic. So they spend the next part of the book arguing about how can they fix this system in Frege. And he is dead set on writing a book with Whitehead, which we'll discuss next time. So here's basically the plan. Mathematics must be based on logic. Frege creates the right logic based on sets. I find a paradox. Logic is faulty. Whitehead and I must fix it. The Principia. Principia Mathematica we'll discuss next time is an attempt to try to fix the problem in Frege's system. Whether or not Principia succeeded, we'll have to discuss next time. But this is, and we'll finish the book, we'll spoil it for you on Monday. Any questions?
I think Gödel also uses diagonalization.
We'll do Gödel and completeness on Monday.
Should have seen this coming.
Yes. Okay.